In 1882, Tesla discovered the rotating magnetic field. Tesla adapted a principle for the construction of alternating current AC induction motors and three-phase system for generation, transmission, and distribution of electrical power. While Tesla's invention is widely used today and lighting the entire globe, it also created a reactive energy with negative impact on power quality, losses, and power transmission. In time domain, there is a phase difference between the current and the voltage due to reactive energy. ELSPEC's engineers have dedicated their work in finding a solution on how to minimize the negative effect of the reactive energy. By using a sophisticated solution which is based on real-time static VAR compensation, they have succeeded in limiting this effect. The following vector diagram describes the relationship between the total apparent power expressed in volt-ampere, VA, the active power in watt, W, and the reactive power in volt-ampere reactive, VAR. The graph shows the current and voltage in time domain and in vector domain. In most cases, the loads in the electrical diagram in industrial plants are inductive, created by magnetic fields of transformers and motors. Capacitors banks are used to compensate the reactive energy of these loads in order to comply with utilities' power factor requirements. The following vector diagram and waveform describes the power, voltage, and current with compensation. The solution which is offered by ELSPEC is Activar Equalizer Systems based on Thristor's switched capacitor. The Activar is used for relative stable loads, such as commercial buildings, hospitals, and data centers. The Activar is characterized by slow variations of reactive energy demands. The equalizer is used for fast variations loads, such as plastic and automobile industries, as well as motor startup, cranes, loads, and more. The equalizer is characterized by fast or extremely fast variations of reactive energy demands. The Activar equalizer switches capacitor groups on and off using electronic switches, thyristors. Transient effects typically created by electromechanically switched power factor correction, PFC systems, dramatically reduce the life expectancy of the PFC systems. The advantage of the AC EQ systems is that the connection and disconnection of capacitors occur precisely at zero current crossing. The Activar and equalizer systems always includes reactor, either in detuned or tuned configuration, in order to avoid resonance between the network and capacitor bank, or to reduce substantially the harmonic level respectively. Utilities generate an almost perfect sinusoidal voltage with an extremely low level of harmonics. Harmonics created by nonlinear loads such as variable speed drives, power rectifiers, inverters, etc. These loads cause nonlinear voltage drops and change the sinusoidal nature of the voltage. As a result, the harmonic level in voltage and current is substantially high. Pure spectrum, distorted spectrum. Pure spectrum, distorted spectrum. The diagram shows that the harmonics current flow to the direction of the source. Capacitors are used to compensate the reactive energy. The diagrams show the locations of the capacitors is in parallel to the source. In this case, there is a frequency at which the capacitors may create a parallel resonance with the power source, high impedance. This happens when the internal impedance of the transformer, XLTR, is equal to the impedance of the capacitors, XC. An example of high impedance. The parallel resonance creates very high impedance at the resonance frequency. The graph shows that the resonance frequency is increased if the numbers of the groups in the capacitors banks are decreased and vice versa. If the resonance frequency occurs in proximity of the harmonic sources, resonance may be created. The graph shows two frequencies of 250 Hz, 5th harmonic, 350 Hz, 7th harmonic, where resonance occurs when 6 groups and 3 groups are respectively connected. Resonance may occur on any frequency. However, in most cases, harmonic sources exist in the 5th and 7th harmonics. In order to avoid the resonance, series reactors with the capacitors are used in order to shift the resonance frequency below the 1st harmonic source, which means below the 5th. In this example, the frequency is 145 Hz. It doesn't matter how many groups are connected, it always bellows the 5th harmonic. Harmonics current can be substantially reduced by using harmonic filter. A filter consists of a capacitor in series with a reactor tuned to a frequency which is at the vicinity of the harmonic source, 5% to 10% lower. The impedance of the filter is very low at the harmonic source, and therefore, most of the harmonic current flows to the filter. This way, the harmonic source doesn't flow to the direction of the power source, transformer, and as a result, the voltage is not distorted. ELSPEC offers either harmonic filter for the 5th harmonic or filter for the 5th and 7th in case the 7th is also dominant. The capacitor and reactor parameters are carefully designed in order to cope with overcurrent and voltage caused by the harmonics. The filter can be designed to absorb approximately 80% of the relevant harmonics. It doesn't matter how many groups are connected. The tuned frequency of the series resonance is always the same, approximately 238 Hz, since each group is tuned to the same frequency. Examples of results are showed here. The graph shows the harmonics level in voltage and current without tuned compensation. The harmonics level is substantially reduced with tuned compensation system.
Without compensation.
The graph describes the effect of the tuned system on the harmonics, with or without. The results are substantially reduction in the harmonics level. For summary, the graph shows a comparison between detuned and tuned systems. The series resonance frequency of the tuned system is at the vicinity of the 5th harmonic, 238 Hz, and at 189 Hz for the detuned. The impedance of the tuned system is substantially lower than the detuned. The parallel resonance of both systems is far below the 5th harmonic. The Equalizer ST is a centralized motor startup solution that provides real-time compensation for the motor reactive current during startup. This avoids voltage drop and reduces the current substantially during motor startup period. For low-voltage applications, the EQST is connected directly to the network. One system is used for all motors. At medium voltage application, the EQST is connected using a step-up transformer to the medium voltage network. The size of the step-up transformer is approximately 40% of the EQST, since the EQST is designed to operate during motor startup period only. The starting current of an AC motor usually varies 6 to 8 times higher than the nominal current. This is due to the large amount of energy that is required to magnetize the motor. The high current draw from the network usually causes problems, such as voltage drop, high transients, and in some cases, uncontrolled shutdowns. The left graph shows the active, reactive, and the apparent power, while the right graph shows the current and the voltage drop during motor startup period. The effect of cycle-by-cycle reactive power compensation is shown on the same motor startup. The results during motor startup are substantial reduction in voltage drop and current. The graph shows a comparison between voltage drop with and without compensation during motor startup. The result is substantial improvement in voltage drop. The next demonstration is a 176 kilowatt motor startup at low voltage with inertial disc is connected. The controller shows how all groups are connected immediately and disconnected as soon as the motor reaches its nominal speed. The graph shows the voltage and the current RMS values and waveform during startup with and without compensation. The following diagram is zoom in of motor startup with compensation. All groups are connected immediately and disconnected as soon as the motor reaches its nominal speed. We can see smooth and immediate connection in less than one cycle. When motor startup is terminated, groups are disconnected one by one, while the envelope of the capacitor current follows exactly the envelope of the motor. The results: 85% improvement in voltage drop, 61% improvement in current reduction, and 30% reduction in startup duration.